Okay, so while we wait for more attendees to join us, I will give a brief introduction. So on behalf of Biocytogen, I'd like to welcome everyone to our first webinar in 2023. We're so excited to invite back some of our immunology and pharmacology experts that will provide some insights into our disease modeling capabilities here at Biocytogen, so we can help you to achieve your research goals. I'm Jenna Frame from the marketing team, and I'll be moderating today's webinar and discussion. My scientific expertise spans the use of animal models in the fields of hematology, oncology, and immunology. I'm joined today by our panelists who will help answer any questions you may have after the presentation, including our head of preclinical pharmacology, Dr. Luke Yu, who has more than 15 years of experience in the industry working with multiple drug development programs from preclinical to clinical stages. We're also joined by Dr. Margaret Barlow, who earned a PhD in immunology and currently is a senior business development manager working with our European clients. Finally, I'd like to introduce today's speaker, Dr. Rebecca Soto. Rebecca has a PhD in biomedical sciences from Harvard, where she studied the influence of chromatin modifying enzymes on blood stem cell development. Rebecca will be introducing data from several inflammatory disease models that we've internally developed and performed for our clients. So if this is your first time joining us, if you'd like to ask a question, the Q&A box is open and our panel will address the questions after the presentation concludes. So without further delay, I'd like to invite Rebecca to begin the presentation.
Okay, great. Thank you so much, Jenna, for that. And thank you everyone for joining us for our February webinar, where we will focus on inflammatory disease modeling in humanized cytokine mice. So I'll start by providing a brief introduction to Biocytogen and the services we provide. So founded in 2009, we initially focused on genetic engineering, where we developed proprietary methods that improve gene editing efficiency, even for very large insertions. With this platform, we have been able to supply over 4,000 custom models for both academic and industrial clients. We have since expanded our service platforms to include preclinical pharmacology and therapeutic antibody discovery, which uses our immunoglobulin humanized mice platforms, RenMab, RenLite, RenMab Hits, and our more recently launched RenNano. We use these integrated platforms to help accelerate drug discovery for our clients worldwide. So just jumping into today's presentation, I'll discuss modeling inflammatory diseases such as psoriasis, atopic dermatitis, delayed type hypersensitivity, ulcerative enteritis, and multiple sclerosis in wild type and humanized mice. And I'll finally summarize on how these models can be integrated into drug discovery platforms and can help streamline your therapeutic drug discovery workflow. So beginning with psoriasis, it is a chronic inflammatory skin disease characterized by uncontrolled keratinocyte proliferation and dysfunctional differentiation as a result of an overactive immune system that causes red, itchy patches with scales, most commonly on the knees, elbows, trunk, and scalp. While there's currently no cure, there are treatment options available to help manage symptoms. And the following figure highlights several cytokines that are associated with psoriasis, namely IL-17, which has been shown to activate keratinocyte proliferation in the epidermis. So at Biocytogen, we have developed a psoriasis mouse model to evaluate efficacy of novel therapeutics. In this model, skin lesions are chemically induced using imiquimod, or IMQ for short, which stimulates the overactive immune system in the area to which it is applied. IMQ is topically applied on the dorsal back skin consecutively for 5 to 8 days. Treatment with therapeutics can be given 3 times on days 0, 3, and 6. So in this model build, IMQ induces psoriasis-like phenotype on the dorsal skin after 4 days of exposure. Cumulative and individual erythema and scaling scores indicate that IMQ-induced skin inflammation was visible and increased in severity up to day 4. In contrast, mice shaved and treated with control cream did not show any signs of inflammation. Next, histological analysis indicates that IMQ application induced keratinocyte proliferation and inflammatory cell infiltration, which resulted in significantly increased epidermal thickness skin lesions, and inflammation, which was scored cumulatively in panel C. So, taken together, these results indicate that IMQ application induced a psoriasis-like phenotype in mice. So we next examined the potential efficacy of dexamethasone on improving pathological changes associated with psoriasis. So psoriasis-like erythema and scaling symptoms following IMQ application, which is denoted by the red line, were alleviated by treating mice with higher doses of dexamethasone, as shown by the orange line. Furthermore, histological analysis of these mice also indicated that dexamethasone treatment inhibited keratinocyte proliferation and inflammatory cell infiltration in the skin. Epidermal thickness and overall histopathology scores also indicated that dexamethasone treatment controlled psoriasis-like injury and skin inflammation in a dose-dependent manner, as shown in the bar graphs. So we next wanted to evaluate the efficacy of novel anti-human IL-17 therapeutics for treating psoriasis. So at Biocytogen, we have generated double humanized mouse model that expresses both human IL-17A and IL-17F cytokines. So first, to confirm secretion of human IL-17A, serum was collected from mice stimulated with anti-mouse CD3 and anti-mouse CD28 antibodies in vivo and analyzed by ELISA using a species-specific IL-17A kit. In panel A, mouse IL-17A was detected in wild-type mice, while human IL-17A was exclusively detected in homozygous double humanized IL-17 mice. Similarly, to validate the expression and confirm secretion of IL-17F, CD4 positive T cells were sorted from splenocytes and induced into Th17 cells using PMA and ionomycin. Panel B shows that mouse IL-17F was detected in supernatant from wild-type mice, while human IL-17F was exclusively detected in our humanized mouse model. So to test the efficacy of novel antibodies targeting the human IL-17 pathway, psoriasis was induced with IMQ over a 6-day period in double humanized IL-17 mice. Beginning on day 0, bimekizumab, an anti-human IL-17 antibody, was intermittently dosed at both low and high doses. Shown using the green and blue curves here, anti-IL-17 treated mice have an overall reduction in skin erythema and scaling. Additionally, histological analysis showed that higher doses of the anti-IL-17 antibody reduced disease severity as indicated by decreased epidermal thickness and histology scores. So taken together, these results show that bimekizumab prevented psoriasis-like lesions in our double humanized IL-17 mice in a dose-dependent manner. So like psoriasis, atopic dermatitis is a chronic skin disease that clinically presents with itching, redness, dry cracked skin, and small raised bumps that can become infected if irritated. They can appear anywhere on the skin, and repeated scratching can cause thickening and hardening of the skin. AD is thought to stem from a dysregulation of the immune system, resulting in the heightened production of inflammatory signals that damages the skin barrier, particularly type 2 cytokines such as IL-4. There's no cure for AD, and treatments consist of topical steroids and behavior modifications. So at Biocytogen, we have developed a protocol to model atopic dermatitis in mice, which has been validated in various strains to evaluate efficacy of novel AD therapeutics. So in this model, skin lesions are chemically induced using oxazolone, beginning with a sensitization period on day 0, followed by challenges 3 to 4 times a week from day 7 to day 25. Mice were treated with therapeutic agents twice a week beginning on day 6. So in this mouse model of AD, we monitored ear thickness and serum IgE production following oxazolone administration in wild-type C57 black 6 mice. Looking at the data in red, both show a significant increase compared to the vehicle control. Additionally, Histological analysis demonstrates that oxazolone administration induces stromal cell proliferation and inflammatory cell infiltration in dermis and subcutaneous tissue. For example, eosinophil infiltration significantly increased in oxa mice, indicative of atopic dermatitis-like pathology. So in the second study, efficacy of the steroid dexamethasone was assessed in mice with AD. In a dose-dependent manner, dexamethasone treatment reduced ear thickness and serum IgE levels compared with the oxazolone-only group. The high-dose treatment, shown by the orange line, completely relieved ear skin edema to levels similar to the control. However, it was also associated with significant weight loss compared with the control group, as shown in panel A. And lastly, serum IgE levels suggest that medium and higher doses of dexamethasone may slightly reduce the overall concentration of serum IgE compared with the oxazolone-only group. Next, H&E staining of mouse ear tissue sections again indicated pathological changes related to atopic dermatitis, including thickening of the dermis and mixed inflammatory cell infiltration. However, these phenotypes were significantly alleviated in the dexamethasone treated groups, especially in the high dose group, which is 0.09% dexamethasone, which ultimately returned to baseline. And the eosinophil infiltration score in the skin was significantly lower in the dex treated groups than in the oxazolone-only group. So overall, dexamethasone improved atopic dermatitis related symptoms, with the higher concentrations of having the most efficacy. So we next wanted to evaluate the efficacy of novel anti-human IL-4RA therapeutics for treating atopic dermatitis. So Biocytogen has generated a double humanized mouse model that expresses human IL-4 and IL-4RA cytokines. So to confirm secretion of human IL-4, serum was collected from mice stimulated with an anti-CD3 antibody in vivo and analyzed by ELISA, using a species-specific IL-4 ELISA kit. In panel A, mouse IL-4 was detected in wild-type mice, while human IL-4 was exclusively detected in homozygous double humanized IL-4 mice. Similarly, to validate protein expression of IL-4RA, splenocytes were isolated from wild-type and homozygous double humanized IL-4 mice, with and without stimulation, and were analyzed by flow cytometry using species-specific anti-IL-4RA antibodies. So in panel B, we see that mouse IL-4RA was detected in wild-type mice, while human IL-4RA was exclusively detected in our humanized mouse model. So in this next study, efficacy evaluation of dupilumab, which targets IL-4RA, was assessed in an AD model using Biocytogen's double humanized IL-4RA mice. Measurements of ear thickness indicate that the highest concentration of dupilumab, shown in light green, could improve ear skin edema compared with the oxazolone plus isotype control group, which is shown in red. Similarly, higher concentrations of dupilumab significantly reduced serum IgE concentrations, suggesting efficacy in mitigating AD phenotypes. Additionally, dupilumab treatment alleviated some of the pathological changes related to atopic dermatitis. The eosinophil infiltration score in the skin was significantly reduced in the high-dose treatment groups. And together, these results indicate that our double humanized IL-4 mice provide a powerful preclinical model for in vivo efficacy evaluation of anti-human IL-4 receptor alpha antibodies. And lastly, we next wanted to evaluate the efficacy of novel anti-human TSLP therapeutics for treating atopic dermatitis. So we have generated a double humanized mouse model that expresses both human TSLP and TSLPR cytokines. So first, to confirm secretion of human TSLP, calcipotriol was first topically applied on the ears of wild-type and homozygous double humanized mice for 7 days. Ear grinding supernatant was collected from mice and analyzed by ELISA using a species-specific TSLP ELISA kit. In panel A, TSLP was detected in wild-type mice, while human TSLP was exclusively detected in homozygous double humanized TSLP mice. Similarly, to validate protein expression of TSLPR, macrophages isolated from wild-type and heterozygous double humanized TSLP mice were analyzed by flow cytometry using species-specific anti-TSLPR antibodies. Panel B shows that mouse TSLPR was detected in wild-type and heterozygous double humanized TSLP mice, while human TSLPR was exclusively detected in humanized mice. And so, like our previous AD experiments, in this mouse model, skin lesions are chemically induced using oxazolone, beginning with a sensitization period on day 0, followed by challenges 3 times a week from day 7 to day 25. And in our homozygous double humanized TSLP mice that were treated with an anti-human TSLP antibody by IP injection, we see that tezepelumab administration in OXA-treated double humanized TSLP mice improved ear thickness and reduced the concentration of serum total IgE levels compared with the oxazolone plus isotype control group. And so lastly, treatment alleviated some of the pathological changes related to OXA-induced atopic dermatitis, such as ear thickness and eosinophil infiltration. So taken together, these results indicate that our double humanized TSLP mice provide a promising preclinical model for in vivo efficacy evaluation of anti-human TSLP antibodies. And so another form of skin irritation occurs via allergic contact dermatitis, which is a type 4 or delayed type hypersensitivity response by an individual's immune system to a small molecule that contacts a sensitized skin area. The resulting antigen-specific T-cell mediated response triggers a cytokine-induced proliferation process that in turn creates a localized inflammatory response. Building on our previous methods by using OXA to chemically induce skin lesions, we additionally established a model using keyhole limpet hemocyanin, or KLH, which is a large copper-containing protein that is highly immunogenic, T-cell dependent antigen. And so like our OXA model, skin lesions are chemically induced using KLH, beginning with a sensitization period on day 0, followed by a single challenge on a later date. So ear swelling responses were analyzed by immunohistochemistry, as shown in panel A. Particularly change in ear thickness was significantly reduced in OXA-induced DTH mice treated with either an anti-TNF alpha antibody or dexamethasone, compared with the OXA-only group, which is consistent with our previous studies. And so we next wanted to examine whether dexamethasone treatment similarly alleviated KLH-induced DTH symptoms. A reduction in ear and epidermal thickness measurements were observed in KLH mice treated with dexamethasone. So together, these data indicate that DTH can be successfully induced in wild-type C57 black 6 mice using either OXA or KLH and can be therapeutically treated with dexamethasone. So I will now pivot to ulcerative enteritis, which is an inflammatory disease of the digestive tract. So inflammatory bowel disease refers to chronic inflammation of the colon or gastrointestinal tract, which includes ulcerative colitis, Crohn's disease. And clinical symptoms of IBD include recurrent diarrhea, abdominal pain, intestinal bleeding, fever, and weight loss. And so while disease pathogenesis is not clear, it typically involves epithelial permeability, followed by bacterial entry and immune activation that ultimately results in expansion of the lamina propria due to a cytokine imbalanced and chronic inflammatory state. So acute ulcerative enteritis or chronic colitis can be chemically induced by dissolving dextrin sulfate sodium, or DSS, in drinking water. Water supplemented with DSS for 7 consecutive days destroys intestinal epithelial cells in mice, releases cytokines by nonspecific immune cells, and finally results in disruption of the integrity of the mucosal barrier to recapitulate the disease. Clinical assessment and pathological features in DSS-induced mice include weight loss, loose stools, and granulocyte infiltration measurements. So in this mouse model of IBD, DSS-treated mice experienced decreased weight changes, which correlated to an increase in disease severity as indicated by a high DAI score. Therefore, we next wanted to assess the efficacy of cyclosporin A at mitigating the effects of IBD. DSS-CSA treated mice controlled body weight changes and DAI scores altogether. And so this altogether suggests that cyclosporin A relieved IBD-related clinical symptoms in a dose-dependent manner. Next, colon evaluations at the study endpoint indicated that mice given DSS alone had shorter colons and altered weight ratios, shown by the green bar. However, mice exposed to DSS and treated with cyclosporin A did not exhibit significantly different colon length and weight ratios when compared with the control group. So this indicates that CSA treatment helps prevent the onset of disease symptoms in DSS-induced IBD mice. Next, histological analyses of the colons in DSS-treated mice showed significantly disrupted morphology, such as hyperplasia or thickening of the lamina propria and inflammatory cell infiltration. However, these phenotypes are significantly alleviated by treatment with cyclosporin A in a dose-dependent manner. Altogether, DSS-induced IBD was successfully established in wild-type C57 black 6 mice, and cyclosporin A treatment could significantly alleviate experimental IBD-like colonic lesions. So while DSS is widely used to recapitulate human IBD in mice, several preclinical models exist to study various aspects of disease onset and progression. So in this pilot study, CD4 positive, CD45RB high naive T cells were isolated from male and female C57 black 6 mice and adoptively transferred into 9 to 11-week-old female skid mice that lack T and B cells. So specifically, the CD4 positive, CD45RB high population contains naive T cells that are primed for activation, which can induce chronic small bowel and colon inflammation. So here we see that adoptive T cell transfer induced IBD was successfully established in skid mice, as shown by body weight loss, which correlated to an increase in disease activity index score, shown by the green line, and altered stool consistently compared with the PBS and CD4 positive control groups. Next, gross anatomy and histological analyses of the colons in T cell transplanted mice show significantly disrupted colonic weight to length ratio and morphology, such as hyperplasia and inflammatory cell infiltration. So together, these data indicate that in addition to DSS, CD4 positive, CD45RB high adoptive T cell transfer can induce IBD in skid mice, which recapitulates pathological features of human IBD. And so for our last inflammatory disease model, I will discuss multiple sclerosis. So multiple sclerosis is a chronic inflammatory disease of the central nervous system that leads to encephalitis and demyelination. Autoreactive T cells and B cells are activated in peripheral lymph nodes and migrate through the blood-brain barrier, where they are further activated by local antigen-presenting cells. These processes induce cytokine and chemokine production, facilitating the entry of other cell types from the peripheral blood. At the central nervous system, macrophages and activated T cells attack myelin components and release cytokines that activate B cells, which mature to antibody-producing plasma cells. This increases the inflammatory response and causes demyelination and axonal damage. MS results in symptoms such as muscle rigidity and paralysis, visual disturbance and blindness, sensory loss and ataxia. So at Biocytogen, we focus on the development of active EAE for testing therapeutic interventions. Mice are immunized with myelin oligodendrocyte glycoprotein, or MOG, emulsion for prolonged antigen release, and sensitized by PTX injections. Fingolimod treatment started on day 12, which is around the time that symptoms begin to manifest. So in this study, EAE was induced in wild-type C57 black 6 mice by immunization with MOG, emulsion, and PTX. Compared to vehicle control, MOG PTX-treated mice displayed higher clinical scores, which reflects tail weakness, lameness, high limb paralysis, and other symptoms. The disease also induces weight loss, as shown on the left. However, fingolimod treatment controlled clinical symptoms in a dose-dependent manner. Additionally, spinal cords were isolated 28 days after MOG emulsion and PTX injections and analyzed by H&E staining. Compared with the vehicle control, inflammatory cell infiltration decreased in MOG PTX mice, but was controlled with fingolimod treatment. Together, this data demonstrates successful induction of stable EAE disease in wild-type C57 black 6 mice, and that fingolimod treatment alleviates disease severity. So in addition to the inflammatory disease mouse models I have discussed with you all today, we also offer other inflammatory disease models, including rheumatoid arthritis and asthma, for your in vivo efficacy studies, where we have established protocols and defined readouts. And in addition to the humanized mouse models used in the study shown today, here are some other humanized models that may be of interest for inflammatory disease modeling. Or if you have a broader interest in immuno-oncology targets, there are many other strains of humanized immune checkpoint mice that we do offer. We welcome you to visit our website for the full list of strains, including multigenic humanized immune checkpoint models, or you can also download our full catalog using the QR code on the bottom, or reach out to us after the webinar if you're interested. And again, today I discussed different inflammatory disease mouse models, but we also offer a variety of metabolic disease mouse models. And so stay tuned for a future webinar if you're interested in those. And so whether you're interested in inflammatory disease modeling, essentially our services at Biocytogen are fully integrated and can support your research needs from target to IND. So whether it's gene editing services, our full catalog of animal and cell models, pharmacology service, or antibody discovery services. So with that, I would just like to thank you all for attending today's webinar. If you have any questions following, please feel free to reach out to us either via our website at biocytogen.com or email us at info@biocytogen, or feel free to call us. But thank you so much for tuning in today.
Thank you, Rebecca. I'd like to invite our panelists to join for the Q&A session. Hopefully we'll have some more questions rolling in. And thanks, Rebecca, for that wonderful presentation. So taking a look at the Q&A, there's a question about the cross-reactivity of these monoclonal antibodies that we're using in the disease models. So I assume that this is with respect to human versus mouse cross-reactivity. So the question is, can you attribute the efficacy of dexamethasone exclusively to inhibition of the human cytokines and not the mouse? Any of our panelists like to answer?
Should I reply this? Yeah, okay. So we did use this dexamethasone in both wild-type mice and humanized mice. Both showed a very good efficacy. So that means the dexamethasone definitely can cross-react with the mouse and and the human immune system.
Yeah, and I think, using the dexamethasone in the humanized mice, I think we really want to demonstrate that the humanized mice are no different than wild type. We can still establish the disease model, and it appears to function in the same way that it would in the wild type mice.
That's correct.
Okay, so next question. Have you conducted any atopic dermatitis models with ovalbumin? If so, were there visible changes to dorsal skin thickening, and some other detailed questions about ovalbumin?
So I mean, from the data we presented today, we did oxazolone treatment. But if anyone is interested in using ovalbumin, we're happy to discuss with you what kind of inflammatory disease modeling you may be interested. So yeah, absolutely feel free to reach out if that's what your research needs are.
Let's see. Question about whether our models are adapted for cell therapy product investigation. Would anyone like to answer, or should I jump in?
I mean, you have had oh, sorry, go ahead, Luke.
Rebecca.
No, I was just gonna say, we can. We've had a recent webinar series. I believe it was the end of last year, where we talked about NK cell therapy. So we definitely have those services available.
Definitely, that's a very interesting area to use cell therapy for the inflammatory disease. So for our capabilities, most of the time we use cell therapy for the immune oncology, and also some project is ongoing for the inflammatory disease. So maybe we'll have some results coming soon.
Okay, yeah, stay tuned for that. Okay. Let's see, next question. So there's a question related to the mouse cost. And so I know we get a lot of cost questions. I think that those types of questions, our business team will work with you to determine the specific needs for your experiment and the models that you need, and then work with you to develop a specific quote for your study. Does anyone have anything to add to that?
I would just add that like the costs can, it just depends on the specific model, especially if you're looking at like a humanized model, whether it's like a single target or double target. Yeah, we can definitely get specific answers to you after we can connect after the webinar for that.
Great. So there's a question here about the role of IgA or IgE in testing of disease, and how the levels may vary from person to person.
There's a lot from animal model, it's from the mouse model, or from about the human. I'm not quite sure. So definitely for the animal models, we did see like as Rebecca presented, we did see IgE level is increased in the model, like a psoriasis model, AD model. We see it in the AD model. We didn't measure IgA level in these models. Definitely there are some IgE related disease, like IgA nephropathy. There's IgA related disease, but we do not have this model available by now. Yeah.
I would just like to say, I think that's also a limitation of some of these models. So we are measuring serum IgE levels, but we found in our studies that we need a large area of the skin to have topical application of our test article to induce serum IgE levels. So.
Okay. There is a question about a humanized mouse model that elicits human IgG. So I can just start by saying, you know, you might be referring to the FcRn mice.
Oh, I'm sorry, what's the question about? There's
A
go ahead.
A humanized mouse model that elicits human IgG.
The IgG, that's like we have our own mice, that's a humanized IgG, right? So to making the human antibody. Also, we have in the ren mice, there's a ren-nit or ren-nano. We have those mice can generate the different human IgG antibody, right? So there's a from ren mice, there's a humanized IgG. For ren mice also that's good for our bispecific antibody generation. Ren-nano mice, that's good for our human nano antibody generation. I don't know if we answer the question. For also we have a humanized FcRn mice. That's IgG binding the receptor. So that's for IgG antibody PK
Recycling.
study,
Yeah.
recycling PK study.
Mm-hmm. Yeah, absolutely. So if you're interested in antibody discovery, ren mice, FcRn could be more useful for PK studies. Thank you, Luke.
No problem.
Okay. So there's a very specific question about the ELISA kit, and I think we'll have to kind of consult and get back to you on that question. And let me just see if looks like there's some more questions coming in. So for the chronic AD model in mouse, what cytokines are most easily measured? Interferon gamma, IL-17. And how do you measure by ELISA?
Maybe I should answer this question because AD model basically is a Th2 cytokine, Th2 type disease model. So most time we measure like a Th2 cytokines like IL-4, IL-5, IL-10, or IL-6. Definitely also in culture we also measure some Th1 cytokines like TNF-alpha. So that's a very common cytokine we can measure in this model. Definitely we have very good capability for in vitro cytokine measurement, like with Luminex. So we Beijing team and the Boston team have very good Luminex assay capabilities. We can definitely work on the test these assays.
Yeah, and if you're interested in the details, there is some more information on our website, or you can reach out to us to discuss more specifics. Okay, there was a question asking about the recording. The recording will be made available on our website. And so, yeah, just keep an eye out for that if you'd like to rewatch the recording. And if you have any further questions, please feel free to reach out to us. Let's see. Reading over the questions, make sure I didn't miss anything. Okay, well, it looks like our questions have all been answered today. So I'd like to conclude today's webinar and thank our speaker and panelists for joining us. And we hope you enjoyed the webinar, and we look forward to speaking with you further about how we can help you advance your research. Thank you so much.
Thank you.
Bye, thank you all.
Thank you.